So let's look now at the qualification program and procurement. So as an example qualification program, let's look at what we did for the normal heat flux panels with the EUDA. So typically the qualification starts from doing very small size sample tests to mock-up tests to then semi-prototype, full-scale prototype, and then eventually leading up to the series production. And typically you test different technologies, materials, design as you go along and validate them at these increasing scales. And you can see at the bottom, along the way, we have conceptual design review to check where we are on the design, the preliminary design review, the final design review. In this case, with the EUDA, we signed the procurement arrangement, the fabrication contract, if you want, in 2017. And now the EUDA has just signed their contract signature with their supplier to start series production. They finished all these up all the way to full-scale prototype. Same things will be applied to the other components. This is just an example. So we have 7 blanket in-kind procurement arrangements. All of them have been signed. We have 2 shield block PAs with China and Korea. They have completed successfully their full-scale prototype program, and now they are in full swing in series production. And we have something like 80 plus shield block now at different stages in the production line. We have 3 first wall panels PA. The one with EUDA, as I mentioned, the full-scale prototype program was successfully completed, and they just signed their contract for series production. In the case of China and Russia, the full-scale prototype program is ongoing. We have 1 blanket module connection PA with the Russian DA. In this case, all the small components required for phase 1 assembly are being shipped to VIO. We've received some already. And the full-scale prototype program is ongoing for other components. We have a blanket manifold PA with the EUDA, and right now they are going through their call for tender for series production. And you can see the 2 examples below. One is a full-scale prototype from Korea for the shield block on the left, and a full-scale prototype for the first wall panel from the EUDA on the right. The blanket manifold system, this is the system that feeds the water to the blanket. The design is being optimized. It is supported to vacuum vessel. It is supported by vacuum vessel. Qualification and R&D tests are ongoing. We have signed the PA already with EUDA a couple of years ago in 2019. Actually, the design is quite complex because of interface and EM load constraints. It's not just designing a bunch of pipes. For example, the support to pipe connections has to be thermally conductive because you want to basically transfer the heat generated in the support by the neutron energy deposition to the water in the pipe. But at the same time, you want this junction to be electrically insulating to maintain reasonable EM load. So it is quite challenging to have a very thermally conductive joint, but an electrically insulating one. And you can see the sketch on the right of a blank manifold system, and on the bottom, typical manifold for one sector. And then you have also a picture of a full-scale partial prototype that was manufactured to check the tolerance and assembly of such a component. So to finish, the blanket will be installed in ITER as part of second assembly. For first assembly, which will last, and first assembly leading to first plasma, which will last maybe 6 months of operation. This is more to commission the big items at the back, like the magnets, the vacuum vessel, and other system. And to avoid the complexity of having a blanket there also, the blanket is not installed, nor is the diverter, by the way. So in order to protect the vacuum vessel from the plasma, we have first plasma protection components that are being designed and are being procured now, consisting of 4 temporary limiter belts, 1 diverter replacement structure, 1 electron cyclotron resonance heating mirror, and 1 ECRH dump. And these will be installed for first plasma operation, and then removed, and the blanket will be installed after that for operation. So in summary, a blanket is essential for the operation of a fusion reactor. ITER will provide a range of key information in the development and operation of blankets for commercial reactors. We're going to learn important information from the ITER blanket itself on a range of topics, including integration, interface management, tolerances, assembly, remote maintenance. And then we're going to have test blanket modules, which will be used to obtain information for demo and beyond. And these will be designed, fabricated, installed, and tested to provide tritium breeding and higher temperature operation information. So the ITER blanket adventure, it has been and is very challenging. This is a first-of-a-kind blanket to operate in a first-of-a-kind fusion reactor. We have to be very organized in order to accommodate so many demanding constraints. We have to be stimulated. It has to be stimulating because we need to generate ideas sometimes to find solutions when issues arise along the way, in particular when dealing with interface requirements. And then in terms of yardstick, we need to have the same yardstick, same one for all interfacing systems so that they can progress at a similar design development level to help solve integration issues. So after all, I started to say that maybe ITER blanket, you won't have quite a cozy feeling, but maybe after all, you do have quite a cozy feeling. So thank you for your attention and goodbye.